basically. Calculate normally. So what do I mean by that? How do you multiply complex numbers? How do you add complex numbers? How do you divide complex numbers? Well, pretty much the same way you did before, right? The derivatives and integrals we'll get to in a second. Now I won't, in here, well, anyway, one thing at a time. So, for example, oh goodness gracious. If I have z equals to, say, x plus iy, and if I have w equals to a plus ib, where here a, b, x, and y are all real variables, if I multiply these complex variables, z times w, how's it go? So my point is you just distribute like normal, all right? So it's like xa plus ibx plus iya plus I squared yb. And then customarily we collect things, all right? So this is like x times a minus yb plus I times bx plus ya. So this is how you multiply two complex variables, for example, right? I probably didn't need to tell you this. You probably could have just figured this out if I just said, how would you multiply them? You would have done this, right? With the understanding that when you have I squared, minus 1, right? Now, there's something else you can do. There's a complex conjugate, z bar. So, for example, if x and y being real, the complex conjugate of x plus iy is x minus iy. This is very, very cool because if you look at 1 over z, right, you can, if z is not equal to 0, if you have 1 over z, you can rewrite that as like z bar over z bar. So multiplying the top and the bottom by the complex conjugate. What's that give us? X minus iy upstairs. Downstairs it gives us x plus iy times x minus iy. What does that work out to? I mean, really, if I was a more civilized human being, I would have told you before I did this that z bar is equal to what? It's right here, right? Yeah, x squared. It's x squared minus I squared y squared. So x squared plus y squared. And you notice the cross terms, the terms with I, they cancel, right? So what is the significance of that? Well, if you draw in the complex plane, right, this is your z, right? So this is x, this is y. Of course, this is we usually use this symbol, the length of the z, thought of as a two-dimensional vector. So this is actually the length squared of the complex number z, thought of as a two-dimensional vector. Anyway, the super awesome, really, really nice thing here is simply that 1 over z is then x minus iy divided by x squared plus y squared, right? And that you could rewrite as x over x squared plus y squared, right? Plus I times minus y over x squared plus y squared, if you like, right? This is the so-called Cartesian form. That's how I started this whole discussion, right? I presented complex numbers like this, things like this. This is the so-called Cartesian form, right? So what this little thing shows you is 1 over a complex number can be rewritten, right, in its Cartesian form just by multiplying by conjugate over conjugate. Now, let me make this a little bit more down to earth. For example, suppose we have like 1 over 3 minus 7i. How can I put that in Cartesian form? I multiply this by what over what? do you think? Minus or plus I? Minus or plus the 7I? Plus. Okay, good. So how did you know that? I mean, what's the rule here, basically? Just flip I to minus I. That's complex conjugation, right? And so what's this give us? 3 plus 7I over what? 9 plus 49. So there you go. 3 plus 7I over, what is that? 58? So I'm okay, guys. If I ask for Cartesian form, you can write it like that. That's cool. Like I mean, there's some people who are like real sticklers. They'd be like, it's not in Cartesian form yet until you write this. I just assume that you guys are smart enough that you realize that you can rewrite what I wrote in purple as what I wrote in red, right? No big deal. There is actually a problem in your homework that asks you to do this. It's a real problem that exists in your homework, okay? So don't be scared of that one. Now, I'm mentioning this because we need to know some of these things as we come up against them. There'll be places where you need to do this, like to move the I from the denominator to the numerator in order to successfully complete a calculation. Let me show you an example of that. So, jumping the gun a little bit, one of the things you're going to show in the homework is you're going to explain why it is that d dt, all right, of e to the lambda t, all right, is equal to lambda e to the lambda t when lambda is a plus ib. Now, I'm not going to teach you the theory of complex differentiation. So in other words, we're not going to learn how to differentiate with respect to a complex variable. What we do in here, what's useful to us, is differentiation of a complex valued function of a real variable. So we take derivatives with respect to real variable of a complex valued function. All right, it's really, really complicated, so I want you guys to pay close attention how this is defined. Here we go. So a complex valued function of a real variable looks like this, u plus iv. So like here, u and v are both functions of a real variable. The way this is done is du dt plus I times dv dt. You should complain, I'm being condescending. You already know this. This is the differentiation you learned in Calculus 3. This is how we differentiate like a vector valued function of a real variable, right? Component-wise. Same thing, just new notation. I separates the first component from the second component, right? There's a natural correspondence between z equals to x plus iy and the two-dimensional vector x comma y. All right? Anyway, that's the definition. So, So, I mean, the other thing I tell you, all right, is that if we have like e to the x plus iy, what we're going to say is we're going to say the definition of this, basically, is e to the x times e to the iy. And this guy is, in fact, cosine of y plus I times the sine of y. So this is what's known as, this is the so-called the complex exponential. That's how you take the exponential of a complex number. It's actually a combination of ordinary real exponentials and sines and cosines. Let me bring this down to earth a little bit. So I ask you to prove it in general in your homework, all right? But let me show you a specific example of your homework here. So for example, if I'm going to calculate d dt, right, of e to the 3 plus 2i times t, what does that mean? that means we're differentiating, so that's e to the 3t plus 2it. So in other words, think x equals to 3t, think y equals to 2it in up here. Right? So what I'm really differentiating is e to the 3t cosine 2t plus I e to the 3t sine 2t. Yes, Luke?
Sorry, can you explain again how we got from e to the iy to cosine and sines?
I can. It's a definition. All right. But there are reasons for that definition that we'll get back into as the semester progresses.
To IT, wherever you have the cosine 2t. Or, oh wait, no, it's in the...
Nope, the only I is right there.
Okay.
So this is the Cartesian form of this complex function. Right? This is like the u I was just talking about. This right here, the coefficient of I, is like the v I was just talking about. So to differentiate a sum of real functions with an I, you just differentiate with respect to time and basically think of conceptually I is independent of time, right? So it just rides along. And you have, well, but it's ugly, right? So this is 3e to the 3t cosine 2t minus 2e to the 3t sine 2t plus I times 3e to the 3t sine 2t plus 2e to the 3t cosine 2t product rule. And then what I do is I'll go, okay, so I got a 3e to the 3t, and I'll collect my cosine and my I sine. So check it. We got one here, and we got one over here, and this I. So that gives me cosine 2t plus I sine 2t. Then I've got a minus 2, right? Actually, I'm going to say plus 2i. And now I could be a little bit 2i. There's an e to the 3t. I'll pull that out. That's everywhere. Now I got to use your imagination a little bit right here. I factored out 2i. Well, one thing I don't need to use my imagination for is this cosine 2t term, right? That's just cosine 2t. See, because there's an I. See this I here? So I times cosine 2t gives me cosine 2t with the 2i out front. But over here, see this minus right here? We have to reinterpret that as what? Trade that minus 2 for a plus 2i squared, right? We can rewrite this as plus 2i squared. And with that in mind, if I factor the 2i out front, I get plus I sine 2t, right? And then just factor, you get 3 plus 2i times e to the 3t times cosine 2t plus I sine 2t, which, by the way, is just 3 plus 2i e to the 3 plus 2i times t. This is a non-trivial identity. Folded into this single innocuous expression is product rule and the derivatives of sine, cosine, and exponential all at once, plus the structure of complex multiplication. There's a lot of data in this. But it's really, really, really interesting what that allows you to do. I don't think I can say more today, but I'll show you how we can use that to do things like, for example, I can integrate e to the x sine x dx using this stuff without doing integration by parts, just by straight integration. So maybe I'll show you how to do that at the start of next class. Now, you don't find much of this in standard books. But the truth of the matter is, to really understand the techniques we do this semester, you have to take a complex perspective. We don't need the full bore canon of complex variables, right? So if we just know some like basic manipulative complex variables, this stuff that, without proof, just sort of common sense calculation like I'm showing you, you can go a long, long ways. Notice that the point of this was not that you do it that way, right? The point of this is once you understand, you don't have to do it that way. You can do it like this, right? You immediately go from here to this. So I hope you understand the point of this calculation is not that we should keep doing it that way. It's that it's true and it's nothing mystical. It's just this worked out. That's all I was trying to say. So anyway, thanks guys. I hope that's enough for you to do the last couple homework problems. Email me if it's not. And I will shut up.